All right, let's get a sense of how quantum mechanics is applied to electrons. We're going to start by taking a look at quantum numbers. Think of quantum numbers as an address system. Okay, it's a way of finding electrons. It specifies what energy level, what sublevel, what orbital, and where in the orbital those electrons are. Okay, Schrodinger came up with our first three quantum numbers, and they describe the main energy level. They describe the shape of the orbital and the orientation of the electron in that orbital. The fourth energy level describes the state of the electron, and it took a couple of other scientists to come up with this last one. So the first quantum number is called the principal quantum number. It's represented by the letter n. We've already been using it. N equals 1, n equals 2, etc., etc. Those are all examples of the principal quantum number. The main energy level or shell occupied by the electron, that's what n tells us. So hydrogen's electron, its only electron, is in the first energy level, so its n value is 1. Okay. Once you get to lithium, for example, we have 3 electrons in lithium. The first 2 are in the first energy level, n equals 1, and the last one is in the second energy level, n equals 2, and so on and so forth. Okay, so the values of n are all positive integers, 1, 2, 3, 4, 5, 6, 7. As n increases, so as n gets bigger, the size of the orbital is larger. In other words, the electrons are further away from the nucleus. They have more energy. And the electron's average distance from the nucleus is increased. Okay? So it kind of looks like this. Now, they're not all equidistant from the nucleus. You have to understand that. Okay? The distance from n equals 1 to n equals 2 is pretty big. It gets smaller as you go higher in n value. The second quantum number is called the angular momentum quantum number, represented by the letter L. There's no script L in my PowerPoint, so sorry. That's L. L indicates the sublevel of the electron, okay, which is really the shape of the orbital, if you think about it, because each sublevel has different shapes. The number of L values that you can have is equal to the value of n. So if you have a value of n equals 2, that means that there are 2 possible values for L. Because if you think about it, there are 2 sublevels on the second energy level. There's the S, 2s, and 2p, right? So there are 2 values of L. The actual values of L start at 0 and are integers, positive integers, and they go up to whatever the n value is minus 1. So to use as an example the second energy level, n equals 2, that means there are 2 values of L, and the values of L are 0 and 1. Those are the 2 values. Okay? So here's an example. 1s. Okay? N equals 1. There is 1 value of L. Its value has to be 0. We always start at 0 for L. And the first time we see an L value of 0 is on n equals 1. That's the first time we see a sublevel called S. Anytime you have an S sublevel, the L value is 0. So we go to 2s or 3s. We still have an L value of 0 in there. It's just that the orbital is getting bigger as it gets further from the nucleus. If we're on an L value of 1, then we've got p orbitals. The first time we see an L value of 1, the first time L can equal 1 is when n equals 2, because L is equal to 0 up to n minus 1. And so if we want L to equal 1, then we have to have an n value of at least 2. And that's because we don't see p orbitals until the second energy level. There is no 1p. There's only a 2p. Okay? So if n gets bigger than 2, for n equals 3, n equals 4, we still have an L value of 1 in there somewhere. We still have p orbitals. They're just further from the nucleus. They're just bigger. This picture's over here on the left is kind of interesting just to remind you that the 3 p orbitals, px, py, and pz, which are shown here in the middle, they all share the same central point, the nucleus. And so they all kind of come together like that. It's a vaguely spherical shape. If we want to look at the d orbitals, there are 5 d orbitals. There's the dxy, the dyz, the dxz, the dx squared minus y squared, and the dz squared. And they're mostly all cloverleaf shaped except for the dz squared. The L value for d orbitals, for a d sublevel, is 2. And the first time we see d sublevels is in the third energy level, 3d. That's the first time d comes into the picture. Well, third energy level has an n value of 3. N equals 3. So you have to have at least an n value of 3 to have an L value of 2. And when L is 2, we're talking about a d sublevel. The f orbitals, here are all 7 f orbitals, very strange shapes. See, as the energy increases, the shape of the orbital gets weirder and weirder. Okay? F orbitals, there are 7 of them, and they have an L value of 3. And the first time that we're allowed to have an L equals 3 is when n is equal to 4, because L goes up to n minus 1. And so we don't see F orbitals until the 4th energy level anyway, 4F. This is the first time we see them. Okay? As we get higher in energy, there will be other shapes. The Schrodinger's wave equation, you solve the wave function and you graph it and you get the shape. As long as you follow the rules, you'll get other shapes. So there would be G orbitals, for example. There would be 9 of them, and they would start at n equals 5 if you had electrons that had enough energy to be in there. Same thing with H orbitals. There would be 11 of them, and they would start at n equals 6. But we don't have any elements that have enough electrons with enough energy in their ground state to exist in those orbitals. That doesn't mean that they don't exist. And as a matter of fact, when we excite electrons, they might actually go into some of these orbitals. There are pictures of them online if you really want to see what they look like and how weird and bizarre they look. Just Google G orbitals or H orbitals and see the pictures that they look like. But it's beyond what we're going to do here because we don't have any elements that actually use them in their ground state. Okay, so we have an n value equals 1, 2, 3, or 4. The number of sublevels is equal to the n value. Okay, and then the L values are 0, 1, 2, up to n minus 1. So when you have an L value of 0, it's always an S sublevel. An L value of 1 is always a P sublevel. An L value of 2 is always D, and an L value of 3 is always F, and so on and so forth, but we never really go beyond F anyway. The third quantum number is called the magnetic quantum number, M sub L, M with a subscript L. It looks like a 1, but it's actually an L. And this talks about the orientation of the orbital around the nucleus. In other words, which specific orbital you're in. The values of M sub L, the numbers it can be, they're integers, but they go from plus L to minus L. So remember, L is the second quantum number and it has a value, and the values of M sub L are based on that value. They go from plus to minus L. Okay? And it tells you which exact orbital the electron is contained in. Each orbital can hold a maximum of 2 electrons. Okay? That's important to remember. So the total number of orbitals in an atom is equal to n squared for an energy level. Okay? The possible M sub L values for a certain subshell is equal to 2L plus 1. This is just if you want to know how many values there are going to be. Right? It might be helpful to look at some examples to see how this works. So for n equals 1, start over here on the left, n equals 1. If n equals 1, there will be one value of L. It has to be 0 because the largest value of L can be n minus 1. And if n is 1, then n minus 1 is 0. So that's the largest value. When L is 0, we're talking about an S sublevel. So the orbital that goes along with n equals 1 and L equals 0 is called the 1s orbital. Okay? The M sub L value is going to be from positive L to negative L, but L is 0 and it doesn't have a positive or negative, so M sub L is also 0. There's only one S orbital, so there's only one value of M sub L, one orbital. If n is 2, then there will be 2 values of L. They will be 0 and 1. If L is 0, that's an S orbital. So n equals 2, L equals 0, we're talking about the 2s sublevel. And again, there will only be one value of M sub L, it'll be 0, which is talking about one orbital. But if L is equal to 1, that's a P sublevel. There are 3 P orbitals. The values of M sub L will correspond to those 3 P orbitals. If L is 1, then the 3 values of M sub L will be minus 1, 0, and positive 1. Negative L to positive L. That's 3 orbitals. That's the 3 P orbitals. Okay, same thing if n equals 3, we have 0, we have 1, and then we have 2. If n is equal to 3, L can be equal to 2. If L is equal to 2, we're talking about a d sublevel. If we're talking about a d sublevel, there are 5 d orbitals. Well, if you take plus L to minus L, you'll have -2, -1, 0, 1, and 2. There are the 5 d orbitals. Those are the numbers that correspond to those 5 d orbitals. And the same thing happens when n equals 4 and L equals 3. The f orbitals, 7 of them. -3, -2, -1, 0, 1, 2, and 3. Those are the 7 f orbitals. Okay? So far, the first, second, and third quantum numbers are giving us a location to find an electron. Okay? They tell us what energy level, what sublevel it is, and which of the orbitals in that sublevel that electron lives in. Now, go back to the last statement on the last slide. The number of, or 2 slides ago, I guess, the number of, no. Now, remember that each orbital can hold a maximum of 2 electrons. We need to be able to specify which electron we're talking about. Okay? This is just a summary of what we've looked at. Right? Energy level n, there's sublevel S sublevel, 1 orbital, total number of orbitals in that level is 1. If n equals 2, second energy level, we have 2 types of sublevels, S and P. There are 1 s orbital and 3 p orbitals, total number of 4 orbitals in that sublevel. That's n squared. 2 squared is 4. Okay? 3 squared is 9, so there are 9 orbitals total on the third energy level and 16 on the fourth, and so on and so forth. Okay? The fourth quantum number allows us to distinguish between the 2 electrons in the same orbital. It's called the spin quantum number, m sub s. It has 2 possible values. Okay? Plus 1/2 and minus 1/2. Don't worry about what the 1/2 means. The plus and minus are the only important things there. Okay? Paired electrons, if they're paired up in an orbital, they have to have opposite spins. And since the maximum number of electrons in any orbital is 2, they have to be spin opposite. And basically what this means is that we have essentially electrons spinning on an axis. And when an electron spins on an axis, it creates a magnetic field. And that magnetic field either goes from north to south or south to north. So we call it spin up and spin down. Okay? If they're paired in the same orbital, those electrons have to have opposite spins. Okay? So you can't have 2 plus 1/2s in the same orbital or 2 minus 1/2s in the same orbital. And this leads to Pauli's exclusion principle. Pauli's exclusion principle says that no 2 electrons in the same atom can have the same set of 4 quantum numbers. 3 of those quantum numbers can be exactly the same, but the 4th one has to be different. Not necessarily the spin quantum number, but one of the 4 has to be different. Okay? So if you have 2 electrons in the exact same orbital, they'll have the same n value, they'll have the same L value, they'll have the same m sub L value, but their m sub S value, their spin value has to be opposite, has to be different. That's Pauli's exclusion principle. We generally talk about Pauli's exclusion principle as an atomic orbital can hold no more than 2 electrons, and if they are paired in the same orbital, they have to be opposite spins. But this is why. It's quantum numbers.